All right, hello physics friends. So I'm going to go ahead and walk through the kinematics notes real quick. So this is for people who are either missed the day maybe, or just want to walk through it again. Obviously I'm going to go over this front part first. If all you want is a walkthrough, feel free to fast forward until we get to the examples on the back, but I thought I would just go ahead and put it all up here. So projectile motion, this is the type of 2D kinematics that we are going to be looking at. And the definition of this is basically, well, this is really hard to do. The motion of an object thrown or projected into the air subject only to the acceleration due to gravity. So what that really means is that when things are in projectile motion, they're not really going to have any acceleration in the x direction. Once we launch something out of our hand, nothing in this class is going to have rocket boosters. So once that object has become airborne, the only thing that's acting on it is the acceleration due to gravity. This next part is pretty important. It's something that you should definitely know. And that is the fact that the x and y directions are completely independent of each other. That's really important. Both x direction and the y direction operate separately from each other. This is important because it will, you have to do all of your kinematics equations with either stuff in the x direction or stuff in the y direction. You can't have information in the x direction and information in the y direction in the same equation. So that's going to be something that's really important. You have to know that they are independent of each other. So let's talk about the variables. The variables are variables that we've already seen. So we're going to have an initial velocity in the x direction and a final velocity in the x direction. We're also going to have an initial velocity in the y direction and a final velocity in the y direction. We're going to have an acceleration in the x direction and acceleration in the y direction. We're going to have a displacement in the x direction, a displacement in the y direction. We're also going to have time, and there's a reason I'm putting time out here. Time is shared. This is the only variable that you can put in either the x equations or the y equations, because the amount of time that something is in the air is the same for both the x and y direction. So that's kind of your link between those two things. All right, so your equations are the same as they were before. So, and I don't think I have one right here, but I can pull it up online. So they are the same equations that you should have, that you've seen many, many times. I'll show you. Here we go. I'm going to pull it up on my screen. So these equations, these are the equations that we're still going to use. So they're the same, you just need to know whether or not you're using it in the x direction or using it in the y direction. So what's that process again? You must use the 7-step process. So same thing we did for 1D kinematics, we're going to use it for this. So you have to use the 7-step process in order for me to be able to follow your work. It also helps to prevent mistakes and helps to keep you organized. So you are required to use my 7-step process when we do 2D kinematics. I'm going to give you a couple little tips and tricks about it. So as we know, our first step is implicit explicit. So you need to figure out everything that the problem gives you. I like to make 2 columns, and then I typically put time either at the top or the bottom, since time can be used in both. I keep it separate, so I put all of my stuff in the X direction over here, all of my stuff in the Y direction over here. It happens to work out a lot better. Are you required to do this? No, but I do strongly recommend it. I have noticed that people who keep their X and Y components separate over here are less likely to plug in X and Y stuff in an equation together. So can be really handy. Sketches, probably going to be a little bit more helpful. We have 2 different types of problems. We've got a football problem, an off the cliff problem. You can utilize this and you can label all the stuff that you want to. I'm a very visual person. I really like to label it. Sometimes it's really helpful for people to do that. So they might come in handy a little bit more than they did before. Your equations are the same, and its relation.
Alex Allen, please report to Mills room. Alex Allen to Mills room, please.
And it still works the same way. Your equations need to be the actual equations with no numbers in it, just the variables. Then you need to do the algebra as well. Once again, just with the variables, no numbers yet. This is where you put your numbers in the plug and chug. And then the check, of course, you don't have to write anything for it. You just need to mentally look at it, see if it makes sense. So the 7-step process doesn't change. It is still going to be used. All right, so let's actually run through an example problem. My apologies. I am actually holding up the camera with one hand. I'm trying to make it as still as possible. Not very good at this. I need to get some kind of camera stand. All right, so let's look at example problem 1. A football is kicked with an initial velocity of 17 meters per second at an angle of 35 degrees above the horizontal. What is the maximum height above the ground the football reaches? And what is the range of the ball? And what is the total time the ball is in the air? So we've got a 3-parter here. Let's look at one really big red flag. So this number right here has an angle attached to it. That should be a big red flag. This number does not go in any of your kinematics equations. You have to break it into X and Y components. If you see a number with an angle attached to it, that means that that number has both an X component and a Y component. Because remember, so if here's my football. I don't know how to draw a football. I'm just going to draw a round oval. So here's my football. It's being kicked up in the air. We know it's being kicked at 17 meters per second. Here's my ground. And it's being kicked at an angle of 35 degrees up into the air. It's got this X component and this Y component. Remember, X and Y are independent of each other, therefore we actually need to break this apart. So all of that stuff we did in vector addition, that's where that becomes important. So before I even start this process, I'm actually going to go ahead and do that. I'm going to figure out what my X and Y components of this number are. So to figure out my initial velocity in the X direction, which is this guy here, I'm going to go ahead and take my 17 meters per second, and I'm going to multiply it by cosine because it is adjacent to the angle of 35 degrees. And if I do that, I find that my value is 13.9 meters per second. To find my initial velocity in the Y direction, it's going to be 17 meters per second times the sine of 35 degrees. And that's going to be 9.75 meters per second. So now I can actually really get started with the 7-step process. I have broken this down into 2 parts and actually made it usable in my kinematics equation. So we'll go ahead and get started. We'll start by pulling out everything that we know out of this. I just solved for my initial velocity in the x direction, and that was 13.9. We also solved for my initial velocity in the y direction, and that was 9.75. Now let's pull out other things that we know. You know that my acceleration in the x direction is 0, because nothing's propelling it. Once it's in the air, once that football has left the foot of the person that kicked it, it's got nothing accelerating it at all. So that also means that my final velocity in the x direction is also 13.9 meters per second. I know my final velocity in the y direction. That's going to be a negative 9.75 meters per second. The reason for that is that mirror image idea that we did when we looked at 1D kinematics in the y direction. So here's my sketch. Here's my football being kicked. It's got an initial velocity here, and it hits here. So if you think about the velocity in the y direction, it never changes. It's always going in the same direction with the same magnitude because we have no acceleration. However, we do have an acceleration in the y direction. A wonderful thing we call gravity, 9.8 meters per second squared in the negative direction. So if I start, I've got my initial velocity here. As it goes up into the air, since acceleration is in the negative direction, it's going to start to get smaller until it hits this point here. And then it actually, so here it is, little tiny one. It's actually going to flip directions right there. So now it's going to start to go in the opposite direction. Start to pick up speed. So with that mirror image idea that we talked about in 1D kinematics, at any point on this side, if I go exactly across to the other side, the magnitude of my velocity is the same, but the sign is different, so the direction is opposite. So that's how I know what my final velocity is. I also know something special about the top. Remember, whenever an object changes direction from upwards to downwards, we have this instantaneous second moment thing at the top. And that is where there is absolutely no velocity. It has to stop for a second to actually change directions. Acceleration is always negative 9.8 meters per second, but it's changing direction and it's starting to go back down to the ground. All right, well, now we've got way more information than you probably thought we could have figured out, considering the fact that we were only given one number. But look at all this. Woohoo! This is why actually writing out everything you know is really helpful. So many announcements.
Please call the office. Mrs. Snook, please call the office.
So now let's actually take a look at our equations for what we need to do. So part A, we want to find the maximum height above the ground of the football. So we are looking for y. We're looking for this. Now, it happens halfway through its journey, so we're only going to care about this first half of the journey. We can actually use v top as our final velocity in the y direction. So I'm going to take a look at all of my equations, and I'm going to settle on this guy because I know my final velocity is going to be v top, my initial velocity will be what it starts as, and I know my acceleration, and that'll actually give me my displacement. So under my equation section, for part A, I'm going to go ahead and write v top squared equals, oh my gosh.
Abby Apple, please come to the main office. Abby Apple to the main office, please.
So many announcements. Don't they know I'm trying to make a video? All right, plus 2ay. So now I can go ahead and do some algebra to solve for y. So if I do that and I solve for y, I'm going to find that it's going to be v top minus v initial all over 2a. Now I can plug and chug. That's going to be 0 meters per second squared minus 9.75 meters per second squared all over 2 times negative 9.8 meters per second squared. And if you type that out in a calculator, and this is where in class I would give you time to do so, feel free to pause the video, but I'm going to go ahead with the answer. You will find that you get about 4.85 meters. So this is the answer to part A. Now let's go up and see what else we need to do. So what is the range of the ball? Range is we're actually looking to figure out x direction. So this is going to be the range, is how basically the distance the ball travels horizontally. So if we look over here at what we've got in the x direction and we take a look at all of our equations, we will find that there's no way we can figure out x without actually figuring out time. So if I didn't ask you in part C for the total time the ball was in the air, you'd actually need to go ahead and figure that out. But since it's part C, let's go ahead and do part C first. Now, I've got more information in my y direction to figure out time. So I'm going to go ahead and use my y direction. Now I'm going to use VFY equals VIY plus AT. There's two ways you can go about doing this. You can still use V top as your V final. Then you'll get the time it takes for it to reach its height. You need to multiply that by 2. Or since we happen to know our initial and final velocity for the whole thing, you can use that. So I'm going to go ahead and do my algebra. Solve for time. And plug and chug. And if you calculate that out, you will find that the time the ball is in the air is 1.99 seconds. So remember, that's C. So now that we've got that, we can actually head back up. And actually, since we've got time, remember time is a link between x and y. So now I can use that, and I can use what I know in my y direction, and I can figure out x. So I'm going to use my favorite equation, it plus 1/2 at squared. Remember, acceleration in the x direction is 0, so all of that goes away. I don't even need to do algebra because it's already solved for x. So I can just do my initial velocity, which is 13.9 meters per second times 1.99 seconds. And if you pound that out on a calculator, you will find that you get 27.7 meters. So that is how far the ball actually traveled during the kick, and that is part B. So this is one of the two types of questions that you will see. It is a football problem. Now let's do an example of an off-the-cliff problem. So suppose the water at the top of Niagara Falls has a horizontal speed of 2.7 meters per second just before it cascades over the edge of the falls. The height of the falls is 59 meters. What is the water's velocity just before the water strikes the bottom? And what is the distance that the water lands from the cliff? So we'll start out by figuring out our implicit and explicit information. So what are we given? What do we know? First thing that we're actually given is the water speed of 2.7 meters per second. So this is an off-the-cliff problem. I'm going to go ahead and sketch this out while we talk about it. Here is my little water droplets, and down they go. So similar to like Roadrunner and the Looney Tunes, as this guy, if the water droplets kind of come over the edge of the cliff, they're only moving horizontally. So this initial velocity is only in the horizontal direction. It's not flying right here. It's not moving in multiple directions. It's only moving this way. So that is my x direction. So my initial velocity in my x direction is 2.7 meters per second. And my acceleration in the x direction, because guess what? Once it leaves, the current's no longer pushing on it, is 0 meters per second squared, which tells me that my final velocity in the x direction is also 2.7 meters per second. So let's look at what else we've got. So we know how fast it's going. Now, because of that idea that as it heads over the cliff, it's not moving at all in the vertical direction, when it leaves, its initial velocity in the x direction, in the y direction, it's actually 0. And this is occurring on Earth. It's at Niagara Falls, so my acceleration in the y direction is going to be negative 9.8 meters per second squared. And I'm also given how high my cliff is, and that is y is going to be a negative 59 meters. Now it's negative because the displacement of my water droplets is going from here to here. So remember, it's final minus initial. So 0 minus 59 does give you negative. Its displacement is negative. It is going in the downward direction. All right, so that's what I can figure out so far. So now let's look at what we need. We want to figure out the water's velocity just before the water strikes the bottom. Now, I have a final velocity in my x direction. It's going to be moving at a velocity in the y direction when it actually goes to hit the bottom. So this is an example of something where we actually have to figure out both of our x and y components and put them back together. So I now got my VFX, I need my VFY. So let's solve for that to start with. So I'm going to use this guy, VF squared, because I know my initial velocity. Y, put y's in there. I know my acceleration, and I know y. This guy is 0. So when I go down here to do my algebra, it's going to be the square root of 2ay. And I can plug and chug. So that's 2 times negative 9.8 meters per second times negative 59. Ooh, meters. Units. If you plug and chug this out, you will actually find that the answer your calculator gives you is 34 meters per second. But I need to add this negative sign. Remember, this has a plus and minus because my water droplet is going downwards. So now I've got my final velocity in the y direction, my final velocity in the x direction. Now I get to use vector addition and actually add them back together. So we're not done yet. So here is my x vector. Here's my y vector. Here is my final velocity. So I'm going to go ahead and use Pythagorean's theorem. And if you plug and chug that out, you're going to find that your final velocity is equal to, where is it on my answer sheet? 34.1. Now that's super close to this, and if you think about it, that does make sense. So this is obviously not drawn to scale. This 34 meters is way bigger than 2.7 meters per second. So it makes sense that this displacement is closer to this number. We're not done yet. I asked you for the water's velocity. Remember, velocity needs a direction. So you are going to have to figure out an angle. This angle and this angle are both equal. So I can figure out that angle by using my tangent function. So that's 34 meters per second over 2.7 meters per second. And if you actually calculate that out in your calculator, you will find that that is 85.5 degrees. So you can report this in two different ways. You can actually, if you were to give me this angle and say that it is south of east, I would be totally fine with that. You could also say that because these two angles are equal, that it is 85.5 degrees above the ground or above the water. Fine with that as well. So I'm going to go ahead and say that my answer is 34.1 meters per second at an angle of 85.5 degrees above ground. But you do need to show me that answer. I do strongly recommend that you draw this guy out and show me the angles that you're figuring out. That way, if you give me some bizarro directional here, I can kind of follow your thought process. So this could be really helpful. Because if you don't actually give me that and you give me some weird angle that I can't figure out what you measured, I can't give you credit. All right, so that's part A. Part B is what is the distance the water lands from the cliff? So now we are actually looking for this guy. We're looking for our x. Same idea. If we go and we look at all of our equations, we will find that we can't actually get x without figuring out time. So I'm actually going to go ahead and find time first. Also, I have more information in my y direction than my x direction, so I'm going to use that. So I just solved for my final direction in my y, so I'm going to use VFY equals VIY plus AT to get my time. I'm going to go ahead and solve that for time. So we've got VFY minus VIY all over A. And if I plug and chug, I will find that my final is 34 meters per second minus 0 meters per second all over negative 9.8 meters per second. You'll find that it takes 3.47 seconds for the water droplets to actually hit the bottom of Niagara Falls. Now that I've got that, I can go back to my X stuff and I can figure out the displacement. I'm going to go back to my favorite equation because remember all that part is going to go away. My acceleration is 0, so it leaves me with this nice little chunk. I don't have any algebra, so I'm going to write none there. My initial velocity is 2.7 meters per second for 3.47 seconds. And if you pound that out on your calculator, you're going to find that it is 9.37 meters. Ooh, sorry. I'm trying to do this with one hand because I am still holding my phone with my other. All right. This is part A. This is part B. So these are your two major types of questions. This is your football question. This is your off the cliff question. I hope that this does help out for anybody who might be struggling. If these are really helpful, maybe we can go over the problem sets and some of the problems that people are having trouble with. I'm more than happy to make some walkthrough videos. Anyway, I hope this helps. Please feel free to email me with questions, and I will see you all tomorrow.